Now, one day in this unit, we will be focusing on all kinds of applications. I just thought I'd mix in kind of a classic here, but it has a statement that sometimes, if we don't interpret correctly, can make this classic little application too hard. So when we think about the yellow statement, 4 times as many trucks as cars. 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 Now, I don't know if you pondered both of those possibilities. I'm sure that you realize only one of them is correct. So which one is it? 4 times as many trucks as cars. It seems kind of backwards though, doesn't it? But you're correct. Why? I'm almost curious how a student would explain why the bottom one is right.
Because they're saying that if they sell 4 times as many trucks as cars, that means that the amount of trucks, you would need to multiply it through the amount of cars by 4.
Yeah, and if you think about it, like Anna's saying, for it to equal the amount of trucks, the cars is the smaller number. And I know every one of you out there would say, yeah, Miss Naylor, multiply a smaller number to get a bigger number. And that's not backwards. That's actually good basic thinking. Okay? Be careful. I'm not sure how you're processing this morning. Maybe you're saying, yep, that sounds good. But I know there's a couple problems I give you down the road where this simple idea makes this kind of classic problem get all wonky. Okay? So smaller to equal bigger. As Anna said, we have to multiply 4 times the cars to get the trucks. Okay, and then you have the other equation, again, kind of a classic, where you have the sum total. Okay, and whether you solved or not, I know that you can, or you should be able to, real simply do a substitution, and it does work out. Okay, notice that we substituted 4c in for t. All right, so be on the lookout for that type of thing. As far as the homework goes, if you want to check some stuff, a lot of these answers were in the back of the book, but I thought I would still present them to you. Were you okay with the fraction for number 13? If you wrote it as a decimal, that's fine, but basically it can happen. So deal with the fraction or the decimal. Now, if you want to know, I took a peek at the last one, number 38, and, well, if you had it right, we give you a little bonus for the homework check. Okay, this time I decided to give you a little bonus. Now, if you had them in a different order, it's fine. Sometimes people organize those 4 answers.
Why did you get a negative 2 for 38? I had positive 2.
Well, I think my finger accidentally hit the negative button on the keyboard and out popped the negative. Yeah, I even, in my answer key, have a positive 2. So I'll get that fixed for your brothers and sisters. Anything else? Anything that you want to talk about? You're going to see some of these on the take-home mini check. Just one thing about number 38. It starts off with 4 equations. Well, the typical idea is then you have to get it down to 3 equations. You have to get to 3 equations. So you do some canceling. Once you get 3 equations, then typically you turn that into 2 equations. Okay, so in most cases, the rule of thumb is 4 variables, 4 equations, then cancel to 3 variables, 3 equations, and then finally to the happy times with 2 equations. All right, well, we're going to, what it's going to feel like kind of all of a sudden switch gears into a different concept, but you're going to find out that the concept connects directly to systems. Everything in this chapter connects to systems, but now we're going to kind of begin studying other connections to systems. And, that concept is the idea of matrices. We're going to spend a few days talking about matrices. Eventually, we'll connect it back to systems. Now, people sometimes have different exposure or different sort of prior knowledge about matrices. Sometimes it's helpful just to draw one, because then you say, oh yeah, those. But if for some reason you don't have too much exposure to matrices, don't worry, we're going to kind of visit them. We're going to visit them with a little more of a newbie approach. But I'm confident that you'll pick up on a number of these things. And again, on the mini check tonight, you actually will do a few matrix problems. You're going to get them right. Okay, we're just going to go ahead and let you get right to that. Now, that's a matrix. I always like to just show one. It's got some variables in it, but just kind of fancy definition, but important. It's an array. I want you to hear that word. It's an array. What's an array? Well, an array is an organization of numbers. It's an organization of rows and columns. Maybe you wouldn't have thought much of it, but not every group of numbers is an array. We could just have like a bag of numbers, like a bingo bag, and you just pull out of the bag. That's not an array. I know it sounds kind of silly, but when you have an array, when things are organized, it's pretty interesting, the math that you'll be able to do with these. You'll see some pretty interesting math ideas as we get closer to the end of the week that you guys will work with a matrix. Okay, and it's because it's organized. Now, it's always organized with rows and columns, and we call that the size of the matrix. We call that the size of the matrix, the rows, then the columns. Another word for size is order. Careful, if we use the word order, that means the size of the matrix. That means how many rows and columns. Okay, order doesn't mean left to right or something like that. It's just another word for size. Okay, and although this is probably pretty basic, be careful, just right away. How many rows are in this matrix? Make sure your eyes are looking at the rows. 1 row, 2 rows. How many columns? 1, 2, 3. Again, kind of basic, but if you switch those numbers around, then you would have a different ordered matrix. So how many rows? 2. How many columns? 3. We call this a 2 by 3. Again, pretty easy, but make sure you're thinking of it in that order so that the size comes out 2 by 3. Okay, now we kind of got this matrix just hanging out here. Let's do something with it. Let's do a real simple problem that deals with equal matrices. And again, probably in a matter of 15 seconds, you would say, yeah, that's kind of common sense, but I still want to show it to you. If matrices are equal, then the corresponding entries are equivalent. Corresponding entries. I want you to hear that simple phrase. Again, if matrices are going to be equal, then we have to have equivalent corresponding entries. So that's just fancy talk for the numbers in each position, but we call those entries. The numbers in each position would have to be equal. So let's say that the matrix that we had hanging out up here is actually going to equal this matrix that has an x, a 2, a 1, a 4, a 2x, and a 0. And we'll make this our first little example. All right, and again, as I would suspect that you would probably say, but we want to say you're right, is that if these matrices are going to be equal, then the corresponding entry, so the entry that's in the first row, first column, has to equal the entry in the first row, first column. So real simple statement, y minus 3 has to equal x. By the way, we're going to try to find x and y. I should have really said that, but that's kind of our goal here. Okay, now I would imagine your eyes kind of go to another entry that contains the letter y and the letter x, and indeed those two have to also be equal. Again, pretty easy statement that y would have to equal 2x. Now make sure that when you write those two equations down that you realize that that it's solvable. You know, you just made up a nice little teeny tiny system. So if you were asked to find x and y, you'd have to continue on your way. Okay, and this problem is kind of intended that you would feel like you wanted to do a substitution method. I guess you could substitute this way. You could also substitute the other way if you wanted to, but this is a little more straightforward. So 2x minus 3 is equal to x, which of course means that x equals 3. X equals 3. Okay, and then I hope you'll plug that back in so you can get y equals 6. Now we would be able to know how those two matrices are equal. All right, so any comments on equal matrices? All right, again, probably some pretty easy stuff, but nonetheless, let's make sure that we're good with this. Scalar multiplication. Again, there's some language that we're using here that, even though maybe the idea is going to be kind of simple, I want you guys to know what it means to have scalar multiplication. We will discover this through, again, a little matrix problem. Sometimes it can be kind of a pain to copy down matrices because you're just copying down numbers. So I'm trying to kind of cut to the main idea here and minimize how much you guys would need to write down. So let's make this matrix have a 2 out front of a 6, negative 3, a x, and a 0. Now, this is a subtraction sign. So there's a subtraction of a y with a 2x, a 2 and an x, a 5 and a 4. And it'll equal one more matrix here with a y, a negative 2, a negative 22, and a negative 16. Now, when you look at what's written up here, there's two matrix operations. There definitely is a subtraction sign, and I'm basically assuming that you guys understand that, yes, you can subtract numbers. But what's up on the screen is trying to get you to think about what's called scalar multiplication, which also is probably going to be pretty easy. But scalar multiplication is when you have a scalar number. Now, if you're like, what do you mean a scalar number? A scalar number would be like the types of numbers that we've been talking about up until matrices, basically any number that's not in a matrix. You see, numbers that are in a matrix, we would call them rectangular numbers. So if I have a scalar number, a number that's just outside of a matrix, then you can do what you probably would assume. You can distribute it. And in fact, for this problem, we really have two examples of some scalar multiplication, which again, you can do what I would imagine you would assume you can distribute it. Now, I'll share with you here that in a moment, we're going to do a different type of multiplication. Just in a moment, we're going to do a different type. And that will not be the same as scalar multiplication. Okay, but right now, pretty nice and easy. I hope that you're just doubling everything and getting ready to do some simple subtraction. Of course, here you're going to multiply everything by y. I would not multiply by negative y. Of course, if you multiply by negative y, now you just have 4 negative signs. So probably not necessary. Okay, so we just did scalar multiplication, which I know you should be saying seems pretty common sense. Now, when it comes to trying to find x and y, just be smart. Select some entries that are going to help you get x and y. It just so happens that if you look at the first entry, 12 minus 2y equals y, well, that had y written all over it. So I basically would say, why not? You can write down 12 minus 2y equals y, and you got yourself a nice little equation. Again, that should be pretty straightforward. Just make sure that you're solving it carefully so that you can get y equals 4. When it comes for solving for x, you do have options, whichever one seems to jump out at you more, but we need to do something that has an x. I could do this entry. By the way, we would call that the entry that's in the second row, first column. If somebody says, hey, second row, first column, then we're able to be talking about the same entries. And of course, when we do subtraction, we just can subtract those corresponding entries. Okay, so I think we have enough information there to solve for x, especially that we already know what y equals. Okay, so we have ourselves a scalar multiplication problem, which also use some simple subtraction so that we can solve for x and y. All right, what are we getting here? -1, I believe, -1. Okay, now if everything up to this point's kind of been like, yeah, that's pretty good stuff. I mean, that's pretty basic. Good. But stay connected with me here, because maybe what we're going to do here is the one thing today that it's like, whoa, wait a minute, can you show me that again? And it's, it's not this. I forgot that this was also what we did in this problem. I'll give it to you since I wrote it down. So again, addition, subtraction, corresponding entries, as you would assume. Now, as I was saying, stay connected with me here, because this last operation, okay, sometimes it is something that people need a little more discussion. It's matrix multiplication. I'll just share that matrix multiplication is not just multiplying the numbers. Okay, if it was, then I wouldn't be trying to set you up here to focus with me. Matrix multiplication is not just multiplying the numbers. Instead, it's sort of a two-dimensional multiplication. It's two-dimensional, where you actually multiply a row to a column. I'll help you see. So we'll multiply a row to a column, and then you will add. And you should at least feel like that there's kind of two steps here, which is why it's like a two-dimensional multiplication. Let me give you another little tidbit, and then we'll do a problem. If you have two matrices, matrix 1 has some rows and columns, matrix 2 has some rows and columns, just so you understand the notation. We have two matrices. They are being multiplied together. First off, you can only do the problem if those numbers are equal. Those numbers would be the number of columns in the first matrix and the number of rows in the second matrix. Now, I'm not big on just telling you stuff. I'm rather that you understand why. So we'll figure out why this is true. But I still want to tell you it's a little easier just to put it all out here. And it's interesting, these numbers on the outside will end up being the size of your answer. And again, I want you to be able to realize why that's true. Matrix multiplication. Okay. A little more than just maybe what you would assume, unless for some reason this is what you would assume. All right, here's two matrices. The first one's a 2 by 2. It's got a 3, 2, -1, and 4. And the second matrix is a little bit bigger. It's actually a 2 by 3. It's got a -2, 5, a 0, and then a 1, -1, and a 3. Now remember, I also realize that some of you, when you see this, you may remember it from Algebra 2 or from another class that you took, but if for some reason you've never seen it, I'm confident that you can figure it out. First off, as we said, this is a 2 by 2, 2 rows, 2 columns. This one's a 2 by 3, 2 rows, 3 columns. I want to make it pretty obvious or pretty real right away that the two matrices are not equal, but that's okay because these two numbers are the only numbers that have to be equal. So that's good. That means we can do this problem. And maybe more importantly, you can start to see what your final answer is going to look like. Now, I do mean this. This is important and sometimes students like to do this. They will think about the size of their final answer. How do you think about the size? I don't know, maybe you kind of make a matrix of that size. It's empty right now, but it's going to end up having 6 numbers because it's going to be a 2 by 3. Okay, and some people don't do this. They don't kind of sketch it out. They just jump in and start finding the answer. All right, but we have to find 6 answers. All right, you ready? Row, this is kind of the method that's written up there. Row to column. Row to column. Maybe you want to circle them. Maybe you just kind of want to see that. Now, when you circle or see this row in this column, you then will take the first entry and multiply it by the first entry. Now, some people write that down. Some people just put it in their head. But it's going to be -6. But I also will need to, did you see what I just did here? I also will need to multiply the next 2 entries. So 2 will multiply to 1. Now, some people write that down. Some people put it in their head. But there's like a -6 and there's a 2 kind of floating around. And as it says up there, you're going to then add. You're going to add. And of course, that comes out to be -4. Now, the reason we're going to write -4 right here isn't just because that's the first spot. It's because that's the first row, first column. I circled the first row, first column, so my answer goes in the first row, first column. Here's where it can get a little messy because, well, I have an eraser with chalk. Depends on what you're writing with, but we're going to actually continue this process with the next column. So maybe you want to circle it, maybe you just want to focus on it. See how this works? First number is 3, first number is 5. Multiply, get 15. 2, then -1. 2, then -1 gives you -2. So there's a 15 and a -2 that get added together to be 13. And I put that answer in the first row, second column. Okay, and maybe at this point you kind of feel like you want to run with this. Don't let me hold you back. 3 times 0, 2 times 3. 3 times 0 is 0, 2 times 3 is 6. 0 plus 6. Maybe you're just wondering what happens next. Do my pink circles help you see? I will continue to take each row and multiply it to each column. Each row goes to each column. Hey, just make sure your eyes are looking at -1 and -2. Sometimes we see it backwards, but it's the first number, -1, and the first number, -2, and then 4 and 1. So matrix multiplication, it's like two-dimensional. It's two-dimensional because you're multiplying two-dimensional objects. And as you guys will find out in this little study on matrices, there's lots of magical things that can happen. I'm serious, there's lots of magical things that can happen with matrices. I hope you come back to keep exploring that. I know there's different levels of understanding. Some of you would be like, I'm ready, Mr. Naylor. Can you just give me the mini check? But let me just, since we're together, let me take a few minutes and make sure that we're all seeing some of these ideas with multiplication. I don't want you to have to write down tons of stuff. You decide if you want to write this down or maybe just watch. Again, I'm trying to keep it simple. Let's say we have a matrix with 1, 2, 3, 4, 5, 6. Just make it easy to fill in 6 numbers, 1, 2, 3, 4, 5, 6. And I guess we'll just keep the pattern going, 7, 8, 9, 10, 11, 12. As you're going to find out in a moment, it doesn't really matter what numbers you put in your matrix. Okay, because what does matter is that you notice that we have a problem. We got a problem, Houston. Now, listen, make sure that you always multiply row to column. Don't be silly and start to do like 1 times 7, 2 times 8. There's no such thing. You can't just multiply the corresponding numbers. It's got to be a row to column. And you should look at this and say, okay, so what's 11 going to multiply by? Well, see, that's why you can't do this problem. You can't do this problem because we don't have the right size. We don't have the right size. 3 by 2, right? 3 by 2. There was a reason that I said that this number has to equal this number. It's interesting.
For like the first one,
Yeah.
If we were given to it were like the other way around, would we just switch it, or would that be like no solution?
Good. I like that you're, kind of thinking a little outside of the box. It's the second thing he said. If you switch this around, you'll switch these around. You're going to end up with the same problem. What you just discovered there is that matrix multiplication is not commutative. Commutative is a fancy word that you learned back in Algebra 1 that means the order. But, right, Brandon, it won't work. It won't work because these numbers aren't equal because I don't have the right combination. And so, hey, you can't multiply like every matrix together. You can't. And I'd like to show one more here. I have a feeling that you guys would have said, yeah, I would have done that, Mr. Naylor, but I still want to show you. It'll be the last matrix that you got to copy down if you're going to write it down. So I've got a 1, 5, 0. I've got a -3, 1, 4. And then we got a negative 2, 6, a 5, 3, and a 1, 0. Again, we've got two matrices, and they're being multiplied together. Of course, what I hope you're kind of noticing here is that they're obviously of different size, but upon further inspection, they are of the right size. And interesting, if you look at these two numbers that have to be equal, that's good stuff. And these numbers here, you would realize that your final answer is a 2 by 2. Your final answer is a 2 by 2. So, as I hope you would naturally do here, you would realize that there's three sets of numbers that go together. And maybe you just kind of want to check if you're on the right track here. It's 1, negative 2. It's 5, 5. It's 0 and 1. Okay, so it should be negative 2, 25, and 0. This problem is supposed to kind of help you see that zeros can be your friend. If you have some zeros in a multiplication problem, okay, they kind of don't, if you will, affect that answer. All right, so matrix multiplication. Do you have any questions on any of those four nums? Did you get the last two 15s there? Okay. Well, all of a sudden we kind of change gears. This matrix